At first glance, this looked like the kind of earthquake report most people would scroll past. No major city was shaking, no buildings were collapsing, no emergency footage was coming in from the streets, no coastline was suddenly under a confirmed tsunami warning, just a remote point on the map far south of Australia, deep in the Southern Ocean, close to Antarctica. But then the second earthquake appeared. Two strong earthquakes, both around magnitude 6, struck almost the same remote underwater plate boundary within minutes of each other. The first one hit, and then roughly 10 minutes later, another strong shock followed nearby. That timing matters. Because this was not just one isolated tremor in the middle of the ocean. It was a double release of energy along one of the most remote tectonic boundaries on Earth, a place most people never think about, but a place that helps explain how the planet itself is built, stretched, broken, and rebuilt. This happened near the Western Indian-Antarctic Ridge, a long underwater mountain system where the Antarctic plate and the Australian plate system are moving apart. It is not a subduction zone like Japan, Chile, Alaska, or Cascadia. This is not where one massive plate dies beneath another and creates the kind of giant megathrust earthquake that can lift the seafloor and send a major tsunami across an ocean. This is a different kind of boundary. Here, the seafloor is being pulled open. Slowly, over geological time, the crust stretches. Magma rises from below, new oceanic crust forms, the ocean floor moves away from the ridge millimeter by millimeter year after year for millions of years. That process sounds quiet when you describe it on a geological timeline. But it is not always quiet. Sometimes the system locks, sometimes the crust bends. Sometimes a fracture zone takes on more stress than it can hold, and sometimes in a matter of seconds, the seafloor snaps. That is what makes this event worth paying attention to. Not because Antarctica is suddenly splitting apart tomorrow, not because this proves some global chain reaction is underway, and not because every earthquake in a remote ocean has to be turned into a catastrophe. It matters because two strong, shallow earthquakes happened close together along a major underwater plate boundary. And that tells us something real about the stress moving through this part of the planet. The Southern Ocean often feels like the edge of the world. It is cold, violent, isolated, and difficult to study. The winds are brutal, the waves can be enormous, the distances are unforgiving. And beneath all of that water is a seafloor that most people will never see. But that hidden seafloor is not empty. It is crossed by ridges, fracture zones, transformed faults, and volcanic systems. It carries the record of continents breaking apart and ocean basins opening. It is one of the places where Earth's outer shell is still being actively reorganized. So when a double earthquake happens there, even far from land, the correct response is not panic. The correct response is attention. A magnitude 6 earthquake is not small. It is a strong event. In a populated area, it could be damaging depending on depth, distance, building quality, and local geology. Out here in the open ocean, there may be no streets to crack and no buildings to sway, but the energy release is still real. The difference is visibility. When earthquakes hit cities, people record them. Cameras shake, lights swing, alarms go off. The event becomes human immediately. When earthquakes hit the deep ocean near Antarctica, the evidence arrives as data, seismic waves traveling through the planet, recorded by instruments far away from the rupture itself. That can make the event feel less important. It is not. It only means the earthquake happened in one of the least watched regions on Earth. The location is part of the long southern boundary of the Indo-Australian and Antarctic plate system. To the north, the Australian plate interacts with some of the most active tectonic regions in the world, including Indonesia, Papua New Guinea, New Zealand, Tonga, and Fiji. To the south, it meets Antarctica through a network of underwater ridges and transform systems. That southern boundary rarely receives the same public attention as the Pacific Ring of Fire. But geologically, it is part of the same global machinery. The Earth's crust is divided into moving plates. Those plates do not move in a clean, simple way. They collide in some places, pull apart in others, and grind sideways along long fault systems. Every boundary has its own style of danger. Subduction zones can produce the largest earthquakes and the most dangerous tsunamis. Continental collision zones can lift mountain ranges and generate destructive inland shaking. Transform faults can create powerful sideways ruptures. Spreading ridges like the one involved here create new seafloor, but they also fracture, shift, and release stress. This is why the setting matters. A magnitude 6 earthquake on a mid-ocean ridge does not carry the same tsunami profile as a massive subduction earthquake. At a subduction zone, one plate can suddenly shove another upward or downward moving a huge volume of water. That vertical displacement is what can generate a dangerous tsunami. At a spreading ridge or transform fault, the motion is often more extensional or sideways. The plates are pulling apart or sliding past each other. That kind of motion usually does not lift the seafloor in the same broad, violent way. So, based on this setting, this type of event would not normally be treated as a major tsunami threat to distant coastlines. But that does not make it meaningless. The hazard is different. The lesson is different. This is not mainly a coastal emergency story. It is a tectonic systems story. The real question is why this part of the ridge released two strong shocks so close together. When two similar-sized earthquakes happen near each other in both time and location, scientists often describe the pattern as an earthquake doublet. That does not automatically mean something worse is coming. It does not prove a larger rupture is about to happen. But it does tell us the system did not settle with one event. One section broke, then another nearby section broke, or the same connected fracture system adjusted in more than one pulse. That is important because earthquakes are not isolated explosions. They are mechanical failures inside a stress system. When one part of a fault ruptures, it changes the stress around it. Sometimes that change is small. Sometimes it is enough to push another nearby section closer to failure. This is one of the reasons doublets are watched carefully. They show interaction. And interaction is what makes Earth systems so difficult to simplify. The public often wants one sentence: is this dangerous or not? But the honest answer is more layered. Dangerous to nearby cities? No, because there are no nearby cities. A confirmed major tsunami threat, not from what this setting suggests. Geologically important, yes. Worth monitoring, absolutely. This is the kind of distinction that often gets lost online. Some people will exaggerate events like this and claim the entire planet is destabilizing. That is not supported by the evidence. Earthquakes happen every day along active plate boundaries. A remote magnitude 6 event, even a doublet, is not proof of some global breakdown. But the opposite mistake is also common. People dismiss anything that does not produce dramatic footage. That is also wrong, because much of the planet's most important activity happens far away from human settlement. Mid-ocean ridges create new crust. Deep ocean currents move heat around the globe. Polar systems influence sea level weather patterns and long-term climate behavior. Remote faults and ridges help shape the ocean basins that define the world map. The fact that no one was standing above this earthquake does not make it geologically small. It only makes it quiet to us. Below the Southern Ocean, the crust is part of a long, slow record of separation. Antarctica was not always isolated at the bottom of the world. It was once connected to other land masses within ancient supercontinents. Over millions of years, rifting, spreading, and plate motion helped open the ocean gateways around it. The sea floor between Australia and Antarctica holds part of that history. It is not just a dark floor beneath cold water. It is a geological archive. Every ridge segment, every fracture zone, every magnetic stripe in the oceanic crust helps reconstruct how plates moved in the past. And every modern earthquake helps show where that movement is still active today. This is where the macro view becomes useful. A single earthquake is a moment. A plate boundary is a system. A doublet is a sign that the system is adjusting in a more complex way than one clean rupture. That does not require fear, it requires context. The Western Indian-Antarctic Ridge is part of the global mid-ocean ridge network, the longest volcanic and tectonic structure on Earth. These ridges run through the world's oceans like seams. Along them, mantle material rises, magma feeds the creation of new crust, and the ocean floor slowly spreads away from the ridge axis. This is one of the core processes of plate tectonics. Without seafloor spreading, the modern map of the world would not exist. The Atlantic would not have opened the way it did. The Indian Ocean would not have the structure it has today. Antarctica would not be isolated in the same way. The ocean basins, the continents, and the boundaries between them are all tied to this slow but powerful process. And earthquakes are part of it. The movement is not perfectly smooth. The ridge is segmented. Transform faults offset the spreading centers. Blocks of crust move at different rates. Some sections slip quietly. Others hold stress and then release it suddenly. When that release happens under the ocean, especially in a region like this, it becomes a reminder of how much of Earth's activity is hidden from ordinary view. There is another reason this matters from a systems perspective. Modern civilization depends on oceans more than it likes to admit. We often think of infrastructure as something on land: roads, power lines, ports, airports, rail networks, pipelines, bridges, and cities. But the ocean is also infrastructure. Undersea communication cables carry global data. Shipping routes move energy, grain, minerals, consumer goods, and military assets. Research vessels and polar stations depend on predictable access windows. Navigation systems rely on mapped seafloor and stable reference models. Climate science depends heavily on ocean and polar observations. The Southern Ocean may seem remote, but it is not disconnected. It is part of the world's circulation system, part of the climate system, part of scientific logistics, and part of the planetary structure that supports global geography. A remote earthquake there does not automatically threaten these systems, but it belongs to the same physical world they operate in. That is the point. We live on top of systems we do not control. Most of the time, they are stable enough for us to build routines around them. Ships cross oceans, cables remain in place, satellites track weather, seismometers quietly record the planet's movements, maps feel permanent. Then an event like this appears and reminds us that permanence is only a human impression. The Earth is moving, slowly most of the time. Suddenly, when stress breaks, the best way to understand this event is to separate verified observation from speculation. What we know is that two strong earthquakes struck close together in a remote underwater tectonic setting near Antarctica. The region is associated with a spreading ridge system where plates move apart and new oceanic crust forms. The earthquakes were shallow, which fits the kind of brittle deformation expected near ridge and transform environments. What we can reasonably infer is that stress was released along a connected or nearby fracture system. The short time between the two events suggests interaction, but the exact mechanics would require detailed seismic analysis. What we should not claim is that this event proves an imminent global disaster. That line matters. Good analysis does not need to exaggerate. The event is already interesting without turning it into something it is not. It shows us a remote plate boundary releasing energy. It shows us that the southern edge of the Australian and Antarctic plate system remains active. It shows us how easily major geological events can happen outside public attention simply because they occur far from people. And it shows us why monitoring matters. Without global seismic networks, this would be invisible to most of the world. No one would feel it on land, no camera would capture it, no local witness would describe the sound or motion. The only reason we know about it is because instruments recorded the waves traveling through the Earth. That is modern Earth science at work. Not dramatic, not cinematic, but essential. The challenge is that public interpretation often moves faster than scientific interpretation. A map updates, a magnitude appears. People start building theories before the full event is understood. That is why caution is not weakness. Caution is discipline. A magnitude 6 doublet near Antarctica should be watched but not inflated. It should be placed into its tectonic setting compared with historical activity and understood as part of a larger plate boundary system. There may be aftershocks, there may be additional small adjustments along the ridge, there may be nothing larger at all. All of those outcomes are possible. The key is not to pretend certainty where the data does not allow it. The strategic takeaway is simple. Remote does not mean irrelevant. This earthquake sequence happened far from cities, but not far from importance. It occurred on a boundary that helps shape the ocean floor. It took place in a region connected to the long geological separation of Antarctica from surrounding plates. It involved strong, shallow ruptures in a part of the world that is difficult to observe directly. That is enough to matter. Not every important Earth event comes with destruction. Some arrive quietly through numbers on a seismic feed from places most people will never visit. But those numbers are not empty. They are signals. They tell us where the crust is moving, where stress is being released, where the planet is still under construction. The Southern Ocean may look like a cold blank space on the map, but beneath it, the Earth is active. It is stretching, cracking, shifting, and rebuilding itself along one of its great underwater seams. This was not a doomsday event. It was not a confirmed tsunami disaster. It was not proof that Antarctica is suddenly breaking apart in a human lifetime. But it was a strong double earthquake along a major tectonic boundary. And for anyone trying to understand the planet as a system that is not background noise, that is a signal worth reading. This is American Sky Brief. We will keep watching the systems beneath the surface calmly, carefully, and without turning uncertainty into fear.